All right, this video is on resonance in Lewis structures. So before we talk about what resonance is and why it's an important thing, the first thing we need to talk about is that we've been drawing Lewis structures. We know that some Lewis structures exist with single bonds, some have double, some have triple. But the kind of big takeaway point is that single, double, and triple bonds all have different bond lengths, okay? So the distance between the atoms. And that's actually something that may be contrary to popular belief, that scientists can actually measure that, okay? They can actually measure the distance between those atoms, and that is called a bond length. And so for this discussion, we're just going to simply state that single, double, and triple bonds all have different bond lengths. Okay, we'll get into how that relates to other things later. But for now, just knowing that a single bond is different than a double bond, which has a different length than a triple bond. Okay, so we're going to start this discussion talking about ozone, okay, which is O3. So if we draw a Lewis structure for this, which we've done in the past, this should have 18 electrons. O is in the center, because who else would be in the center? And when we start to create this picture of ozone, I see quickly that I'm going to need to form some double bonds, and then I have an electron that needs to be moved. And I end up with a picture that looks like this, okay? So, based on this picture, it appears that O3 has one single and one double bond. Okay, and if you were thinking about the bond lengths in this case, you would think that the two oxygen-oxygen bonds would be different lengths. Okay, and they should have different lengths. Because like we said, one is a single, one is a double, and we just previously learned that a single bond and a double bond have a different length, okay? So it's pretty evident here based on my picture that it sure looks like O3 has a single and a double, so therefore they should have two different bond lengths. However, when scientists measured the bond lengths in ozone, they found that they are equivalent. Okay, and that was a surprise for them, because they said, wait a minute, it sure looks like there's a single and a double bond here, so how can it be possible that the bond lengths are equivalent? They can only be equivalent if they have two of the same type of bond. And that would only be the case if we can make this with two singles or two doubles, and neither of those Lewis structures work. So they were really perplexed for a little while in terms of thinking about how is this possible, until finally they figured out that these electrons in the picture are not stationary, so to speak. Okay, they're moving. And so what the scientists kind of said is, and this is kind of a weird idea, they said, what if these electrons here in this double bond are sometimes spending time right where I have drawn them, but then sometimes they're over here, and then sometimes they're over here, and sometimes they're over here, and sometimes they're over here. Now, I know how we have it drawn, the lone pairs would violate an octet, but knowing that electrons could be moving around, what the scientists said was that those electrons are not stationary, and instead they are resonating back and forth in between the two possible locations for the double bond. And so what they did was they drew this with a double-headed arrow, and they said, okay, sometimes the double bond's on the right-hand side, but sometimes it's on the left-hand side. Now, that doesn't exactly answer the question here of how are the bond lengths the same, until you think about that in this case, if those two electrons could be resonating back and forth between those two places, and there's only two places they could be, right? Those two places are here or here, okay? Here or here. Those are the only two locations for the electrons to be. So what they were able to say was that they could calculate something called a bond length by taking how many bonds are in my picture, okay, and there are 3. Okay, so 1, 2, 3, divided by how many places that those electrons can resonate, which is 2. And what they do is they get a bond length of 1.5. And so what we're saying is that this bond here and this bond here really aren't double and single bonds. They're really a bond and a half, and same with this here and this here. And if they're both a bond and a half, then their bond lengths would be the same. So the takeaway here is that the electrons are resonating back and forth. And the real picture is actually an average of all the places that those electrons could be. Okay, so it's kind of a weird discussion. It's a very weird discussion, but this is what resonance is, and it's going to play a part into when we talk about something being a single or a double bond. It might not necessarily be the case, because if there's resonance, as in O3, where we think we had a single and a double, we actually had 2 bonds of equivalent lengths, which were a bond and a half. So this is a little bit of a strange topic. The most important thing for you to be able to do is recognize when Lewis structures have resonance and be able to draw all the pictures associated with it. So we have 3 practice that we're going to do, and this is drawing all appropriate resonance structures. So in SO3, let's see, we'll do a Lewis structure just like always. So this should have 24 electrons. Sulfur is going to be in the center. My oxygens are going to be around. So we connect. Let's see. I don't have any to add or take away, so I know I'm probably going to end up with a double bond scenario. Oops. And then sulfur's got 2 mini electrons, so if I move both of these, both the other oxygens are in need of 1. So there we go. So in this case, it looks like there's 2 singles and a double. However, what we have to ask ourselves is the question of is it possible for those electrons to be in any other place other than right here? And the answer is yes. They could be here or they could be here. So I have 2 more pictures I need to draw. And once I've drawn the first one, it's pretty simple because I'm just going to move the double bond and then place my lone pairs accordingly. Okay, but we also know, I'm going to run out of room, that the double bond could be here. So when we draw resonance, we're not moving the locations of the atoms, okay? Notice my atom placement stayed the same. We're just moving the double bond to a second location if it's possible that it can be in a second location. Now, what really tricks students is calculating what the true bond length would be in this case. And so remember, it's the number of bonds divided by how many locations it could be in. Okay, so in this case, I have 4 bonds in my picture, right? As drawn, I have a double and 2 singles, but that's 4. So I have 4 bonds, and divided by the fact that they could be here, it could be here, or it could be here, and that's 3 locations. So that's going to give me a bond and a third, but all bonds would be equivalent in the SO3 picture. They'll all be the same length because they're all a bond and a third. And that's really a hard thing for students to understand because they see a double bond and 2 single bonds and they automatically think different bond lengths, but not true because there's resonance in these pictures. In HCO2, I have 1 from hydrogen, 4 from carbon, and 12 total from oxygen. So that's 17, plus I have one more to add, so I have 18. I have a carbon, so carbon goes in the middle. My 2 O's go around it, so does my H. Remember, in this picture, I physically have an electron that I have to add. So I'll add it here. And then my carbon and my oxygen do not have an octet. This is a pretty easy fix with a double bond. Okay, this is an ion, so I should have brackets and a charge. Now, the question is, do I have another location for the double bond? And the answer is yes. Remember, don't move your atoms, okay? Don't change how you've drawn your picture. You're just going to move the double bond. Now, think about this. The double bond can't be here, right? Because you can never have a double bonded hydrogen. The double bond, though, can move from here to here. So in this case, I'm only going to have one additional Lewis structure, or one additional resonance picture. Okay, so now this structure will have a true single bond here between the carbon and the hydrogen. But these two bonds are equivalent lengths. And again, this is where you would take how many total bonds? It's 3 here and here, divided by the 2 locations. So the resonating bond would be a bond and a half. So this is a bond and a half, this is a bond and a half, and this is a single bond. And then NO3, so 5 from nitrogen plus 6 from each oxygen, that's 18, and 523 plus 1 extra is 24. Electrons, N's going to be in the center. My oxygens are going to surround it. Don't forget about the 1 electron that you have to bring to the table, so maybe I'll put it here and fix that oxygen. I definitely know I'm going to need a double bond somewhere, so let's just take those 2 and make one. Nitrogen's got 1 too many, and I've got an oxygen who needs that one, so I'll move it here. And there's my picture for NO3 minus, it's the nitrate ion. Now in this case, you have to ask yourself, how many more places can that double bond be? It can not only be here, it can be here, it can also be here. So I should have 2 more Lewis structures. I draw it with a double-headed arrow. Oop, definitely didn't give myself enough room there. So in one case, the double bond can be here. And then remember, this is the 3rd time I've said this, don't move your atoms, okay? Leave them where you had them drawn. You're just moving the double bond and then fixing your lone pairs appropriately. Okay, so those are the 3 Lewis resonance structures for NO3. If you're talking about the bond lengths in this picture, they're all going to be equivalent because the bond can be resonating in all 3 places. Again, how do you determine it? Well, you count the fact that I have 1, 2, 3, 4 bonds divided by 1, 2, 3 locations. And so again, in this case, we would have a bond and a third, but all bonds would be equivalent. And so that is resonance and Lewis structures and a little bit of a discussion in bond lengths.